Currently, 71% of regular COVID tests, otherwise known as qPCR tests, cost upwards of $100. This can vary greatly across large hospitals, in some cases reaching heights of above $300. In resource-limited areas, X-rays and CT scans can be a more affordable alternative to an expensive test. For example, in Ghana, the average chest X-ray costs only $17, while the average CT scan is about $90. If we can effectively diagnose severe cases of COVID using X-rays, we can increase how quickly patients receive treatment, reduce the resource strain on hospitals, and quarantine potentially positive patients while waiting for a more conclusive test. This may help reduce the rate of transmission and flatten the curve. Because CT scans are more expensive and there's a lack of available data with them, we'll be using X-rays to address this issue.
We're using machine learning because manual diagnosis by eye is error-prone, especially for COVID-related pneumonia. The approach here prevents mistakes, distinguishing cases possibly better than a human doctor, while saving time and resources. Here, we're using a convolutional neural net, which can divide images into classes based on specific features in them.
We wanted to accurately detect COVID-19 and not just any random disturbance in a lung X-ray scan, so we added data from other different diseases to create a machine learning model that classified between people with normal healthy lungs and people with lungs affected by COVID-19, bacterial pneumonia, viral pneumonia, and tuberculosis. We pulled X-ray images from publicly available datasets on the website Kaggle, shuffled them to training validation test sets, and downsized every image to 128 by 128 pixel dimensions to reduce the amount of workload on our model. A training set is used to create the model. A validation set is used to provide checkpoints that gauge the accuracy of a model while training, and a test set is used after training to determine the final accuracy of a model. Because the amount of data we had was somewhat limited, we had to augment our data to increase the number of images and diversify our dataset. We randomly rotated, stretched, scaled, and shifted our images in order to provide a more diverse dataset for our model. First model we attempted to train was a 2D convolutional neural network, which was created from 5 different types of layers. The first, a convolutional 2D layer, extracted features from every image to analyze. Secondly, a max pooling layer reduced the dimensions of the model to focus on only the important elements. Third, a dropout layer randomly killed neurons within the neural network to prevent overfitting, which is a training accuracy that is significantly higher than a validation accuracy. Fourth, a dense layer is a standard layer of neurons. And finally, a batch normalization layer is used to reduce the training time of the network.
For our second and final model, we use transfer learning, and this is a technique where an already trained model is used for new applications, in this case X-ray imaging. In particular, we used the DenseNet 201 model, which had already been trained on thousands of images. On the right, you can see our model architecture. We start with the DenseNet, which extracts the features from the image, the meaningful data points, and it ignores the meaningless parts of an image called the noise. Then global average pooling reduces the dimensionality of the data, further narrowing down our data to just a few of the most important features. Flattening finally reformats these features for the bottom 2 dense layers. These are 2 fully connected layers of neurons, and this is where the model learns the patterns in the features that we've extracted, and this is where it actually decides, is an X-ray image classified as related to COVID-19 pneumonia or not?
We put our trained model into practical use by developing a web application where we can upload an image of the patient's X-ray scan, run it through the neural network, and output the probability of the patient having each of the diseases. In this screenshot to the right, we uploaded a X-ray scan of a patient with COVID, and it successfully predicted that the patient indeed has COVID. Our model could generally outperform a diagnosis done by human eye, and is able to detect various diseases with a much lower cost. So by having these web applications, this model has a potential to be put to use in many places around the world, especially being useful in resource-limited countries.